In September 2017, something small and dark passed close to our sun and then began to leave. It was moving at 87 kilometers per second. And as it went, it did something that objects are not supposed to do. It sped up. Not by much. The extra push was tiny, a nudge you would struggle to measure on anything closer to home. But it was there, and it was real, and it should not have been. The man credited with the discovery put it plainly. Its motion could not be explained using either a normal solar system asteroid orbit or a comet orbit. In physics, an object only accelerates when something pushes it. So the question became very simple and very difficult. What was pushing it? 9 years later, nobody has answered that question. Two respected scientists have spent those years arguing about it in the pages of academic journals, and neither has convinced the other. One of them thinks the answer might be a piece of technology built by someone else. The other thinks it is ice doing something strange. They have both been partly right and partly wrong, and the argument is still open. But that is not the reason we are here. Because while they were arguing, one of them went looking for other objects that behave the same way. Not out in interstellar space, here, in our own solar system. Objects that have been circling alongside us the entire time. He found 6. They are small, they are unremarkable to look at. Some of them are barely 3 meters across. They orbit close enough to Earth that we could send a spacecraft to one within a decade, and one of them we already are. And every one of them is accelerating in a way that no known mechanism can currently account for. They were always there, we simply had no reason to check. It took a visitor from another star to make us look. To understand why one small object caused such a problem, it helps to understand how rare it was thought to be, and how ordinary we now suspect it is. Our solar system does not end at Neptune. Beyond the orbit of Neptune lies the Kuiper Belt, and beyond that, far out in the dark, is the Oort cloud, a vast spherical shell that may contain trillions of comets, all still faintly bound to our sun. Some take tens of thousands of years to complete a single orbit. Some will never come inward at all unless something disturbs them. And things do disturb them. The solar system is not sitting still. We are orbiting the center of the galaxy, and as we travel, we pass through the gravitational influence of other stars. A star a couple of light years away is enough to tug at a comet in the Oort cloud and send it falling towards our sun. It is also enough to do the opposite, to pull a comet away from us entirely and set it loose between the stars. Which means every star system with an outer cloud like ours has been leaking material into the galaxy for billions of years. There may be hundreds of trillions of these castaways drifting through interstellar space. Some estimates suggest that objects from elsewhere pass within the orbit of Neptune in enormous numbers, thousands per day. They are simply too small, too dark, and too fast to see. So for most of the history of astronomy, we knew they had to exist, and we had never caught one. That changed on the 19th of October 2017 at an observatory on Haleakala in Hawaii. The object was catalogued first as a comet. Then, when no coma could be found around it, it was reclassified as an asteroid, the first object ever to be reclassified in that direction. And then the orbit was worked out properly, and the classification problem became much larger than anyone expected. It was travelling too fast to be bound to the Sun. Its path was hyperbolic. Whatever it was, it had not come from here, it was not staying, and it would never come back. The International Astronomical Union had no category for that. They had to invent one. They chose the letter I for Interstellar. And the object was given a Hawaiian name meaning a scout or a first distant messenger, Oumuamua. It was somewhere between 100 and 1,000 meters long. Its brightness rose and fell dramatically over a 7-hour rotation, which told astronomers it was strikingly elongated, a long, thin shape, or possibly a flattened disk. And it was not spinning cleanly about an axis. It was tumbling end over end, the way something does when it has been knocked and never settled. It was also, according to readings from the Spitzer Space Telescope, at least 10 times more reflective than a typical comet. But none of that is what caused the trouble. The trouble was the motion. When a comet swings close to the Sun, the ice inside it warms and turns directly to gas. That gas rushes off the sunward side and forms the tail we recognise. It also acts as a thruster. The escaping gas pushes the comet gently away from the heat, and the comet accelerates. This is well understood, thoroughly documented, and entirely unremarkable. So when our visitor accelerated on the way out, the first assumption was obvious. It was a comet, and it was outgassing, and we would find the gas. We did not find the gas. The Spitzer Space Telescope spent 30 hours staring at it and detected nothing at all in the infrared. No coma. No tail. No dust. For a comet of that size, at that distance, releasing enough material to produce that push, Spitzer should have seen something obvious. It saw nothing. An object was accelerating, and there was no visible reason for it to be accelerating. This is the point where the story stops being an interesting anomaly and starts being a genuine problem. Because scientists did what scientists are supposed to do. They tried to kill it. They went through the ordinary explanations one at a time. Solar wind, the stream of particles constantly flowing outward from the Sun, does push on objects in space. It is a measured, real effect. But for a body of that estimated mass, the push was nowhere near strong enough. Radiation pressure, the gentle force of sunlight itself, was the same story. Real, measurable, and far too weak. Every conventional answer required the object to be something other than what it appeared to be. And that is where the disagreement began. The first explanation came from a Harvard professor named R.V. Loeb, and it is the one that reached the headlines. Loeb's argument was not that the physics was wrong. His argument was that the physics worked perfectly well, provided you changed one number. Sunlight could produce exactly the observed acceleration, he showed, if the object were far thinner than anyone had assumed. Not a rock, a sheet. Somewhere between 0.3 and 0.9 of a millimetre thick. A structure a kilometre across and under a millimetre thick does not form easily in nature. So Loeb proposed that it had not formed in nature at all. He suggested it could be a light sail, a piece of engineering built to catch starlight and ride it from one star system to another. Not a probe aimed at us. More likely a discarded fragment, drifting for millions of years that happened to pass through. It is worth being precise about what that claim is and is not. Loeb was not reporting a detection. He was making an argument from elimination, that every natural explanation on the table failed to fit the data, and that an artificial origin fitted it better. It is a real hypothesis, published in real journals, from a scientist with a serious record. It is also, by a wide margin, the minority position. And the reason it is the minority position is a researcher named Seligman. Seligman's counter-argument was that Spitzer had not failed. It had simply been looking for the wrong thing. Spitzer could detect the signatures of ordinary cometary material: water, carbon dioxide, dust. But some gases are effectively invisible to that kind of observation. Hydrogen is one of them. In a paper published in 2020, Seligman and his co-author proposed that the object was outgassing hydrogen, and that this was why nobody could see anything. The push was real, the mechanism was ordinary, and the gas was simply transparent to our instruments. To produce enough hydrogen, the object would essentially have to be made of it. A hydrogen iceberg drifting between the stars, quietly sublimating in the warmth of our sun. Loeb took that apart within months. He co-wrote a paper asking a straightforward question. Where would such an object form, and how would it survive the journey? He showed mathematically that even in the coldest, densest molecular clouds we know of, starlight in interstellar space is warm enough that a hydrogen iceberg would evaporate long before it reached us. The mechanism worked. The object could not exist. Seligman abandoned the hydrogen iceberg. But he did not abandon hydrogen. The answer, when it came, arrived from a different direction entirely, from laboratory work on ice. In 2023, Seligman met with Jennifer Bergner, whose research pointed at something specific. When ordinary water ice sits at extremely low temperatures and is bombarded with radiation, it does not stay smooth. The radiation breaks water molecules apart and traps pockets of hydrogen inside the ice structure itself. The hydrogen does not escape, it waits. And then, when the ice is warmed and its structure rearranges, the trapped hydrogen is released. Water ice is abundant in space. So is radiation. The conditions required were not exotic at all. They were the default conditions of interstellar space, applied over millions of years. Together, Seligman and Bergner argued that our visitor needed a category of its own. Not a comet, not an asteroid. Something they called a dark comet. An object with a coma that is genuinely present, but genuinely invisible. The explanation accounted for both problems at once. It explained the acceleration because trapped hydrogen escaping from a rearranging ice structure provides a push. And it explained the absence of dust, because an object releasing gas from within its own structure does not need to blast material off its surface the way a conventional comet does. Loeb was not persuaded. He published 2 further papers the following month, accusing Seligman of faulty mathematics and continuing to argue his own case. That argument has never been settled. It cannot be settled because the object is gone. It is now more than 6 billion kilometers away, traveling at 26 kilometers per second towards the constellation Pegasus, roughly as distant as Voyager 1 was when it turned around and photographed Earth as a pale blue dot. We traced its path backwards to try to find where it came from. It appears to have arrived from the direction of Vega in the constellation Lyra. 4 candidate home stars were identified, some as far as 81 light-years away. None of them has been confirmed. We had one object for a few weeks, and we did not get enough data. That should have been the end of it. Except Seligman had asked a follow-up question. And the follow-up question is the reason this story matters. If a dark comet is a real category of object, something that accelerates without any visible outgassing, then it should not be unique to interstellar space. There is no reason the process would only happen elsewhere. So he and Bergner and their colleagues began going back through the orbital data of objects already catalogued in our own solar system, looking for the same signature. They were looking for anything moving in a way that gravity and solar radiation could not fully explain. They found 6. Six objects, already in our records, exhibiting acceleration that is not gravitational, not driven by solar wind, and not explained by any known mechanism. They show no visible signs of outgassing. Several of them are tiny. One is roughly 3 meters across. They look, in every ordinary respect, like unremarkable asteroids. And they are all near-Earth objects. Not out beyond Neptune, not on the edge of the system, close enough that missions to them are entirely practical. The accelerations involved are very small. Small enough that they had been overlooked for years, filed away as measurement noise or orbital uncertainty. Nobody had gone looking for them, because until 2017, there had been no reason to think there was anything to find. It is worth being clear about what these objects are not. They are not moving between planets under their own direction. They are not interstellar. They are not behaving like spacecraft. What they are doing is something much quieter and, in its way, more unsettling. They are moving slightly wrong in a solar system we had assumed we had mapped, and we cannot yet say why. One of them, an object designated 1998 KY26, is already going to receive a visitor. The Japanese spacecraft Hayabusa 2 completed its primary mission and was granted an extension. Its new target is that object, and it is scheduled to arrive in 2031. KY26 is small and spins remarkably fast, a full rotation roughly every 10 minutes. When it arrives, we may finally have a close look at something doing the thing nobody can explain. And it is difficult to imagine that object turning out to be a light sail. We have good radar imaging of it. It looks exactly like a small rock, which is, arguably, the most interesting thing about it, because whatever is pushing it is pushing something that appears entirely ordinary. Since 2017, we have caught 2 more visitors from outside, and they are worth comparing because they cut in different directions. The second, Borisov, detected in 2019, was almost disappointingly normal. It arrived with an enormous coma and tail. The visible cloud was something like 14 Earths across. It was roughly half a kilometre in size. It came no closer to the Sun than the orbit of Mars, and afterwards it began to break apart, which is entirely typical behaviour for a comet of that size at that distance. Its composition was uncommon, but not strange. That matters. It demonstrates that an object from another star system is not automatically an anomaly. Sometimes a visitor from elsewhere is simply a comet and behaves like one and can be explained. The third 3I Atlas arrived in July 2025, discovered by a survey telescope in Chile, and it has been anything but ordinary. It is, by several measures, unlike anything previously recorded. Observations found a coma dominated by carbon dioxide, with a carbon dioxide to water ratio among the highest ever measured in any comet, significantly above the trend for comets from our own system. Its dust scatters light in a way that differs markedly from solar system comets. It carries nickel, and measurements of its water found an extraordinary concentration of a heavy form of hydrogen, the first time this has ever been measured in an interstellar object, and a signature that points to formation in conditions far colder than anything we have on record. One analysis suggests it may be close to 12 billion years old enough that the star system it formed around may no longer exist. It also attracted a great deal of attention, some of it serious and some of it not. Because it was there, and because the question is a fair one to ask, radio astronomers pointed an array at it and searched for artificial transmissions. They found nothing but interference from our own equipment. The result does not prove anything about the wider question, and the researchers were careful to say so. But for that specific object, the answer came back empty, and the scientific consensus has settled firmly on a natural origin. 3 objects, 3 completely different characters. One that accelerated without explanation, one that behaved like a textbook comet, and one whose chemistry looks nothing like anything from our neighborhood. 3 is not a sample. 3 is barely a hint. And that is the real problem. Which brings us to the thing that should genuinely bother you. We did not spot our first interstellar visitor on the way in. We spotted it 40 days after it had already passed its closest approach to the Sun. By the time anyone realized what it was 33 million kilometers from Earth and accelerating away. Telescopes on the ground and in orbit were redirected in a hurry. Within 2 months, it was too faint and moving too quickly for even the largest ground-based telescopes to follow. Everything we will ever know about that object, we learned in a few weeks, by accident, after it had already gone. There are proposals to chase it. A group of researchers has designed 2 possible missions, using gravity assists from Jupiter and a close pass by the Sun to reach speeds high enough to catch up. Both are technically viable with current technology. Both would launch in the early 2030s. Neither would arrive until roughly the middle of the century. There is also a European mission called Comet Interceptor, due to launch in 2029, built on a genuinely unusual premise. It will park itself in space and wait for up to 3 years for a suitable target to appear. It will be the first mission ever launched without knowing where it is going. All of which depends on being able to see these objects coming, and for most of the last decade, we could not. That changed 3 weeks ago. In Chile, on a mountain called Cerro Pachon, sits the Vera C. Rubin Observatory, an 8.4-meter telescope carrying the largest digital camera ever built. On the 30th of June 2026, it formally began the Legacy Survey of Space and Time, a 10-year survey that will scan the entire southern sky every few nights, repeatedly, for a decade. The scale is difficult to convey. On a single night in February this year, during testing, it issued 800,000 alerts to astronomers. It is expected eventually to produce up to 7 million a night. During preparation alone, it turned up more than 11,000 previously unseen asteroids. This is precisely the instrument the problem requires. One estimate suggests it could detect dozens of objects like our first visitor. Interstellar arrivals may stop being once-in-a-generation events and become routine. But there is a detail in Rubin's own history that says something uncomfortable about how thin our vision has been. On the 20th of June 2025, the very first night of its science validation observations, Rubin pointed at a patch of sky and recorded our third interstellar visitor, 11 days before anyone announced its discovery. It did not notice. The pipeline for handling fast-moving solar system objects was not yet running. The data sat there, correct and complete and unread. Researchers went back afterwards and reconstructed the observations by hand, using custom techniques, and confirmed what was in them. Their conclusion was blunt. Had the survey started sooner, and the analysis been operational, Rubin might have been the first to greet humanity's third interstellar visitor. We had it. We simply were not looking properly yet. And there may already be a fourth. In June, an object was flagged in Rubin survey data from April and May of this year, identified by linking together detections that the automated system had not connected. It was submitted to the Minor Planet Center as a potential interstellar visitor. At the time of writing, it has not been confirmed. Then there is the sting in all of it. Researchers have run the numbers on whether Rubin will actually deliver a target we can reach. The results are sobering. For Comet Interceptor, the mission already built and waiting, the estimated chance that the survey finds a reachable interstellar object is roughly 0.07%. A more capable mission concept could reach perhaps 3 to 7 of them over the decade. That concept has not been approved. We built the most powerful survey telescope in human history. It will find these objects by the dozen, and we still, most likely, will not be able to catch one. So where does that leave the acceleration? unresolved. Loeb has not withdrawn his argument, and Seligman has not withdrawn his. The Dark Comet model is the mainstream position, and it is a good one. It explains the push and the missing dust with ordinary chemistry, and it has the enormous advantage of predicting something that was then found. 6 times in our own solar system. Seligman's model explains the push with ordinary chemistry, and it predicted the 6 before anyone found them. That is a serious point in its favour. But Loeb has never conceded, and his argument is not that it is aliens. It is that an object this strange earns the harder question, and that natural explanations are being assumed rather than proven. Both of these people know this object better than almost anyone alive, and they still do not agree on what pushed it. That is where the science actually sits. Not on an answer, but on a disagreement. Not because it is comforting, but because it means the universe was hiding something ordinary in plain sight, and it took an object from another star to point at it. In 2031, a spacecraft that has already completed one mission will arrive at a 3-meter rock near Earth that is moving very slightly faster than it should be. It will take pictures. It may settle the question. It may not. Somewhere between now and then, Rubin will almost certainly find another visitor, and this time we will see it coming. We have been able to detect objects from other star systems for 8 years. 8 years out of 4 centuries of telescopes. Every one we have caught has been unlike the last, and we have caught 3. And we have no idea whether that means our solar system is unusual, or whether we simply have not seen enough of anything to know what usual looks like. 6 small objects are circling near Earth, accelerating gently, for reasons we cannot yet name. They were doing it before 2017, they were doing it before anyone was watching. We only found them because something came in from the dark, did something impossible, and left before we could ask it anything.